How do robots see? How are robots able to turn the environment and all the different complex aspects that come to it and convert it into code that a computer is able to calculate and work out where it is and how to maneuver around its environment? You may be used to proximity sensors, commonly in vacuum robots, where they're able to click against a wall and physically interact with the wall to be able to determine if there's an object in front of it. Or, if you are more advanced, you may know about supersonic sensors, by sending out a sonar signal that is able to bounce the signal off walls to determine how far away these walls are by timing how long these signals take to come back. Well, these are great ways of traversing an environment, but they're not good if you need to have more in-depth details, like in self-driving cars, where you can't have them crashing into each other, and you can't have the inconsistencies of supersonic sensors. So how are we able to get robots to do self-driving? Well, this is by replicating the human eye. In this video, we're going to explore some more complicated, in-depth theories of computer vision and these applications in real life. If you haven't seen video 1, please go check it out. It's very cool. It goes over the basics and the setup of how we can do the basics of computer vision and take pictures and track objects. In this video, we're going to work out depth using computer vision. How far away is an object just from seeing it from a camera? Like, can you tell how far away I am? I could be 10 miles away, I could be 10 centimeters away, you don't know. How can we tell? With cameras. That's what we're going to talk about in this video. First, we're going to be talking about stereo vision. Stereo vision is the theory of having two cameras, and if two cameras are looking at an object and they're looking at the same object, they should have an intertwined cross section when they cross over it. If I'm looking at this pen, my eyes have a cross section, they both look at it, and as such, we know the angles. We know the angles of where these are cameras, these eyes are looking at. And we know the distance between the cameras of the eyes, the baseline. We can use trigonometry to calculate how far away it is. Here are the calculations. As you can see, we first have the baseline on the top. This is the distance between the cameras. For my example, I'm using the owl, as seen in the previous video, which has a baseline of 0.067 meters, the distance between the two cameras. Now we use this equation, distance equals the baseline over the tan of the left angle and minus tan of the right angle of the cameras, as you can see down here. As such, we can straight away learn the distance of the object from the system, from the owl. And this is the simple basic idea of stereo vision. As long as the cameras are tuned correctly and as long as they're calibrated correctly, we should have accurate readings. Now we know how to find out the distance of an object. We first need to locate the object. For this, we'll be using template matching. As you can see in this example, we have a template as seen in the top left. This is an exact image we're looking for. And on the image, there's lots of different birds that are very, very similar to the template. But we're looking for a very similar match. For my code, I look for over 80% match. Even though they look very similar, and you can say these birds look almost 90% similar, to a computer, they are in completely different positions. They look completely different to each other using even the different shades of the lighting, meaning that they are completely distinct from each other. As such, it's able to recognize this image, which is really good for us tracking a perfectly identical object and the same object that won't change in its environment, but does have limitations if the object does change, if it moves in 3D space or if the lighting affects it too much. That's why we have an 80% tolerance rate. So if the lighting does change, it still will be able to find the object. It isn't looking for it to be exact, but 80% confidence that it is the right object. We can now construct a working prototype. In this example, you can see the owl, which uses two cameras to represent stereo vision. It also takes a picture of a target, which I held up with my phone, and I press spacebar to take a picture of this target. This is a distinct target. We're using the test dummy image, as it's not like any other picture in its environment, so hopefully we'll be less likely to get misidentification with other things in the environment. With this object detected, both the left and right camera view on the screen. And then I move the object back and forth and at various different angles to determine if it is tracking effectively. As such, I put the phone at known distances along the meter ruler, 10, 20, all the way to 100 centimeters. And with each one, I am observing on the computer whether it is corresponding correctly, if our readings are working. And I turn the angles as well to determine it's not just a fluke that it works straight ahead, but it also works when it turns. And overall, it's able to successfully track the object. One of the first improvements I made was to the actual user interface. Here you can see an example of me holding it up. where you can see that I've written both the left and right angles onto the screen, and I've also added the estimated distance at the bottom, which was proven to be effective. For this test, I put it at a still position at first to show that it is working stationary and it's not jittering, and then I hold it at different angles and I shake it about to see if it works over different movements. And as you can see, over fast moving things, it can easily glitch out and be distorted through lens distortion. And at different lighting values, as the lens focuses and unfocuses, it drastically changes what the image looks like and can sometimes cause it to stop identifying the object. But overall, it is successful at tracking the object. It's just not 100% consistent and does stop and start. But it does continue to recognize the image at both close and far away distances, and is still able to estimate the distance effectively, proving that we do have a working product, and it is very user-friendly. But due to lens distortion, it isn't always having that successful tracking and sometimes loses focus. To fix this issue, I converted the feed to grayscale. This only needs to be done for the computer, but I've done it for the user interface so it's easier to see. As you can see, instead of representing the values of RGB, meaning red, green and blue, it's all in grey. This is because it's using the grayscale, where each pixel is represented on a brightness level ranging from dark grey to light grey. And as you can see, it is much better at targeting the target and staying tracked onto it. But it has a weakness that is continuing from the previous version and into the grayscale. And that is, if the image is rotated, it's unable to recognize the target, as it's only used to it seeing it in its original form, not it rotated. To fix this issue, I implemented the greatest improvement. This is the ability to take multiple template images. Rather than taking one image and looking for this match throughout the feed, we take multiple images first, and it looks for all of them simultaneously and finds the best match of any of them. And if the best match is over 80%, then it will recognize the target. This helps when the target is moving in a rapid moving environment, as it's able to recognize it from different orientations. There is other methods of incorporating this, but they are more very high tech and very high computing power, where it's able to rotate the image in the template. But a simple solution is just to take multiple template images. And as you can see, it works brilliantly for this example. As many people use facial detection is good for when you have to have a distinct image because your face looks like no other. But as it constantly turns and moves and contorts, it will drastically change the image. By having the multiple images, it's able to have a better understanding and have a higher chance of getting an accurate reading. With this task now complete, we're now going to move into the final, most complicated task for this project. This is disparity mapping. Disparity mapping is another way of determining depth of objects, but it's also not able to tell you just what one object is by tracking it, but it's able to determine all the objects in the room. Because even though you know that I'm here and the wall is behind me and the shelf is in between me and the wall, how is a robot going to be able to tell this? One example is disparity mapping. The best way I can explain disparity mapping is if you have two eyes and you look at an object and you close one eye and then you close the other. And as you see, they shift slightly. This is because your eyes are looking at two different positions. They aren't in the middle, you're not a cyclops. You have two different eyes looking at two different images. And your brain naturally combines them into one image. That's why when sometimes you can cover up something and you can still kind of see through it, and it's because one eye can see something that another eye can't. This is your depth. This is how humans compute depth. And it's one reason why if you do lose one eye, you are unable to drive cars legally in the UK, as you lose your depth perception, and it means you might crash your car more. This is how we calculate depth, by using these two different images. So from our previous stereo vision, where we were able to triangulate something with two images, we can now see the different shifts of images and try and calculate like what objects are where and what shifts have occurred, to try and calculate what depth they have, just like the human eyes work. As disparity mapping is very complicated, you can't just simply write code and run it and it works. You first have to run test parameters to align the cameras. As they're controlled with servo motors, they are seeing stuff at slightly different angles. They aren't seeing the same thing. And there is slightly different calibrations where they aren't exactly perfectly looking straight, due to standard human or mechanical error. As such, we first calibrate it. This works by taking 30 pairs of pictures. Each of them are looking at the same object. This chart, this map, you may call it, helps the computer recognize the image and know what it looks like from various angles. As we check it from both the angles, it's able to do the computing that our brain does when it works out the depth of an object, but it's able to do it itself and work out how to align its eyes and work out how depth is and how items look at different angles. When we compute this, we finally get a result. We first get the RMS value, which is the root mean squared. This shows how closely estimated the image points align with the actual detected checkerboard. And the lower the score is, the better the result is. As our score is 0.449, which is less than 0.5, it means that it is less than 0.5% inaccurate, which is a good result, meaning that the alignment is true. And the second result we get is the average epipolar error, meaning how well corresponded the points are from the left to the right image aligned horizontally. And as we see, we got a low value, very close to 0.5 again. It shows that we have a low epipolar error, meaning that we get an overall good result from our pictures. Now that we have finished calibration, we can now run the code. As you can see on the left side of the image, you can see me in real life in the normal camera vision that humans can see. On the right side, you can see the disparity, where the different things in the foreground and the background have different shadings, different levels of grey. Where you can see the meter ruler is light, my body is a bit darker, and things in the background are white or random different colours. And then we have a black background which ignores the things that are really far away. As you can see, it's able to correctly identify the disparity. It's able to correctly identify that there is different levels of stuff. But now we need to actually calculate the distance between stuff. To do this, we use a simple equation. That is, distance equals the constant value divided by the disparity. Now, the distance is what we're looking for, so we need to know the disparity and the constant c. Well, the disparity is something you can read. It's the level, this is the light level you can see on the screen. It's that concentration of the colour. As such, we can just get a classic reading, as you can see down the left side of the chart. Where the middle of the chart is the distance. It's what my meter ruler is. And on the right side, you're getting the constant value. As such, we're getting ones for each different levels from close and far away, as there is a slight change in the constant value. As such, we're able to average it to get a constant value average for the whole distance we're looking for. As we're looking for things between 10 and 100 centimetres, we get a good average disparity that helps it be accurate across this range. It may not be perfect for close range or far range, but over this range, this whole 100 centimetres, it should be good. It may not be perfect, but it should average out a lot better. And in my testing, it actually resulted in a much better system, as overall it reduced our errors to only 3% rather than over 15%. Now that we have the average constant value, we can now calculate distance using this equation. As you can see on the screen, we have combined it into one big window, where we have the distance of the middle pixel at the top of the disparity window, we have the average disparity and the average distance in this white square, in the white border. This is a 50 by 50 pixel range. The reason for the averaging is at the top you can see the distance of the middle pixel. This can be affected by noise. As you can see, there is a distortion. It's not a perfect grey image, this disparity, due to noise and lighting errors. If we just base our distance over one pixel, if there's errors, it could result in false readings. So we average the disparity over the whole square to get average distance readings. And as you can see, we're getting a good average value and average distance, and we're able to successfully measure the object distance. So, in conclusion, we were able to first make a successful stereo vision system by using first template matching, which took a picture of our desired object, and then we were able to search the environment for this object with matching levels to see if we had confidence levels that exceeded over 80%. And then we took multiple pictures of this object and was able to run them all simultaneously to get better readings. And we also converted it to grayscale to allow to stop distortion. And then secondly, we did disparity mapping, where we were able to use 2 points of view of cameras to make a disparity map, where we were able to see the foreground, the background and objects in the room in disparity mapping form. And we were able to successfully do this and know the distance of the objects over the average middle of the area, overall resulting in a successful project with testing and vigorous work put into this to make it a successful product that is ready for industry. And it has so many future applications, not only in autonomous cars and other vehicles, but the future of robotics. So whatever your computer vision journey may take you, I hope these 2 videos have helped you build the foundations of what computer vision can do, and a small insight of the advanced techniques that computer vision can do. And I hope that you can make a successful product that is able to integrate this technology into the future.